Let's now talk about a very important concept which is applied in several chemical reactions. That is the concept of reversibility of chemical changes. The world believed that all chemical reactions were irreversible until 1803, when the French chemist Claude Louis Berthollet introduced the concept of reversible reactions, also known as the concept of reversibility. In the beginning, he only knew that sodium carbonate and calcium chloride reacted to yield calcium carbonate and sodium chloride. But after observing that sodium carbonate formed around the edges of salt lakes, he realized that large amounts of salts in the evaporating water reacted with calcium carbonate to form sodium carbonate, which means that the reverse of the reaction occurred. Chemical reactions are represented by chemical equations. These chemical equations typically have a unidirectional arrow to represent irreversibility or irreversible reactions. Other chemical equations may have a bidirectional arrow that represents reversible reactions. As children, we learned that chemical reactions occurred when reactants reacted with each other to form products. These unidirectional reactions are known as irreversible reactions. In other words, irreversible reactions are reactions where the reactants converted to products and where the products cannot convert back to the reactants. These reactions are essentially like baking. The ingredients acting as the reactants are mixed and baked together to form the cake, which acts as the product. This cake cannot be converted back to the reactants. The reactants in this case are egg, flour, and so on. Just as the products in an irreversible reaction cannot change into the reactant. As stated above, the cake cannot be uncooked, and so the reaction is irreversible. A real-life example of an irreversible reaction is combustion. Combustion usually involves the burning of an organic compound. An example of organic compounds are hydrocarbons. Hydrocarbons are compounds containing hydrogen and carbon only. These organic compounds react with oxygen to produce carbon dioxide and water. Since water is stable, it will not react with the other product, that is carbon dioxide, to form the reactants. Combustion can take the following form. We have CXHY, standing for the formula of any hydrocarbon, with the X and Y being positive integer, such as 1, 2, 3, and so on. This hydrocarbon reacts with oxygen to yield carbon dioxide and water, while a reversible reaction is a chemical reaction where the reactants form products that in turn react together to give the reactants back. Reversible reactions will reach an equilibrium point where the concentrations of the reactants and products will no longer change. In reversible reactions, the reactants and products are never used up. In fact, they are both constantly reacting and being produced. A reversible reaction is denoted by a double arrow pointing both directions in a chemical equation. For example, a two-reactant, two-product equation would be written as thus. We have A reacting with B to give rise to C and D. A plus B are the reactants, while C plus D are the products, with the double arrow being the sign for a reversible reaction. Let's consider another example of a reversible reaction. This reversible reaction can be broken into two reactions, that is, reaction 1 and reaction 2. These two reactions are occurring simultaneously, which means that the reactants are reacting to yield the products, as the products are reacting to produce the reactants. Collision of the reacting molecules causes chemical reactions in a closed system. After products are formed, the bonds between these products are broken because the molecules collide with each other, producing sufficient energy needed to break the bonds of the product and reactant molecules. Below is an example of the summarized form of a reversible reaction and a breakdown of the reversible reaction. So we have N2O4 decomposing to give 2NO2. The reaction 1 and 2 happen at the same time because they are in a closed system. Looking at this picture, we will see reaction 1 where the N2O4 decomposes to give 2NO2. On another reaction known as reaction 2, where it is instead the 2NO2 which is decomposing to give the N2O4. The blue ball represents nitrogen, and while the red ball represents oxygen. To get the third reaction, which is reaction 3, we need to combine reaction 1 and 2. And if we combine reaction 1 and 2, we will obtain a reversible reaction where the 2NO2 decomposes to give N2O4, and N2O4 also decomposes to give the N2O2 back. Now, let's imagine a ballroom. In a ballroom, let reactant A be 10 girls and reactant B be 10 boys. As each girl and boy goes to the dance floor, they pair up to become a product Once the 5 girls and 5 boys are on the dance floor, one of the 5 pairs break up and moves to the sidelines, becoming reactants again as this pair leaves the dance floor. Another boy and girl on the sidelines pair up to form a pull-up once more. This process continues over and over again, representing a reversible reaction. Thanks for your kind attention.